Good evening, ladies and gentlemen, and welcome to Astronomy on Tap Atlanta. It is my honor and privilege and genuine excitement to introduce a fourth-year astrophysics PhD student from Georgia State University who studies the nearest, smallest stars, which means she studies the most abundant stars that this universe makes. She's also a recipient of the NASA Graduate Research Fellowship, which is extremely hard to get. The National Science Foundation, the NSF Graduate Research Fellowship, that last letter that I can't remember. She got a very well-paid position from NSF that is very competitive and not many of us get, so please give her a round of applause for getting that. And she is also a very, very tall, standing, bright pillar of GSU's many outreach endeavors, including Astronomy on Tap and our K-12 outreach endeavors with the Georgia Outreach Team for Space. But that's enough about me. Please, everybody, give one more round of applause for Madison LeBlanc.
Okay. Thank you, Justin. Thank you all for being here. I'm really excited to talk to you all about asteroids. Yeah, let's get started. I need to make sure that this works because I always go the wrong way. So I want to start this talk by telling you all about the difference between an asteroid and a comet. And this is kind of an easy one, so some of you might know this already, but that's okay. An asteroid is basically just a big giant rock. It's a big rock, it's out in space. They have a huge range of sizes between 1 meter and 530 kilometers. So big difference. We have some really tiny ones, some really huge ones. And these are just kind of rocks that are hanging out in space doing whatever, orbiting the sun. And then comets are a little bit different. They're similar. They're also rocky, but they are big rocks with ice and gas inside of them. They have this ice and this gas because they're a little bit farther away from the sun than asteroids are. And they give us this tail when they get close to the sun. So when they get pretty close to the sun, we get this, they start to melt and the sun heats up all of that ice and that gas. And they start to get this tail out the back end of them, which is pretty interesting. This is like when you see a comet on the sky, you see a big long tail behind it. For the sake of completion of this, I also want to tell you about the difference between a meteor and a meteorite, because it's different from a comet or an asteroid. It's a little bit similar. Meteors are a little bit similar to both of these things. So meteors are just those big, you might see these like streaks coming through the sky. You might hear about a meteor shower. These are little pieces of comets or asteroids or whatever rocks are out there in space coming into our atmosphere, burning up when they pass through our atmosphere. So they're pretty tiny, but they, when they burn up, they leave these trails behind them, and they usually will happen, quite a few of them at a time. So you'll hear about a meteor shower. The meteorites then are what happens when they get to the ground. So as soon as those meteors, if any of them do make it to the ground, then that's considered a meteorite. And those are just the pieces of rocks, of space rocks that we find on the ground here on Earth. So today we're going to be talking mostly about asteroids. I'll tell you a little bit about comets, and we're not really going to be talking all about those two things. So don't worry about that. As far as where these asteroids that we're going to be talking about are located in our solar system, we have a diagram of the inner solar system right here. So Jupiter's the farthest out. We got the sun in the center, of course. And we're mostly going to be talking about these near-Earth asteroids here. These are asteroids that cross through the orbit of Earth's orbit, so they kind of have a similar path. They intersect with our path sometimes. And these are the ones we usually worry about when we're worried about what's going to hit Earth, because they're coming so close to Earth's orbit. And then there's this main belt of asteroids. This is where most of the asteroids spend their time. So most of the asteroids are out there in the main belt. They're not crossing through Earth's orbit, but they're somewhere between Mars and Jupiter. And then we have up here, up there are comets that usually come in from the Oort cloud. So the reason why they're so cold and icy is because they spend most of their time far away from the sun in their orbit that's highly eccentric, way out there in our solar system where they have all this ice. And then sometimes when they get close to the sun heats them up and that gas and ice melts, comes out the back of them, and we get those tails on our comets. So that's where we're at in our solar system. We're mostly going to be talking about this red circle in the middle, our near-Earth asteroids. So I want to give you guys a brief history of these near-Earth asteroids. They've been around for a while. We've been concerned about them for a while. Some scientists might say, that the dinosaurs were the first creatures to know about asteroids. Others might say they didn't know what hit them. So yeah, 65 million years ago, that kind of thing happened. Try not to think about that too much. And then in 1801, we discovered Ceres. And Ceres is interesting because Ceres is not an asteroid. Ceres is technically a dwarf planet, but Ceres is located in the asteroid belt. So Ceres was the first object we discovered in the asteroid belt. Mostly because it's really big, so it was easier to see. That's going to be a common theme of this talk. If something is bigger, it's easier to see and easier to find. And so in 1801, we discovered Ceres. That's pretty cool. So now it's like, okay, there's other things out there in the solar system that are not planets that we should maybe be concerned about. And then in 1980, there's about 9,000 asteroids known. So not too long ago, 50 years ago, we had about 9,000 known asteroids. And these two guys are geologists. Their name are Walter and Luis Alvarez. They're a father-son geology duo. And they're really cool because they were studying the line in the rock, like right after where the dinosaurs died, so right after the Cretaceous period. And they were kind of like studying this rock, doing their geology things, and they realized that there was this extra layer of something that they didn't really know what it came from. So like it shouldn't really have been there. They're like, this is kind of weird. We don't know what this is. It was an extra layer of iridium. And they were like, we don't know what this came from. So they start studying it, and they're trying to figure this out, And they come to the conclusion that it is from an asteroid impact in the Earth. So they said an asteroid killed the dinosaurs. That's why the dinosaurs all died at the same time. We figured it out. And everybody else is like, I don't know about that. They don't believe them because there's no, we don't know about any craters on Earth. So they're like, if an asteroid this big killed the dinosaurs, where's the crater? Like, where's the proof? Eventually we found the proof and we figured out it was an asteroid that killed the dinosaurs. So these guys were right. But that was a little bit alarming to have somebody come out and say an asteroid destroyed an entire like species of everything that was on Earth. Like that's kind of scary to think, oh no, now we know what happened, and there's 9,000 of those things out there too. So if you weren't concerned, you probably should be. And so the United States, the European Space Organization, all these space organizations are like, we should probably figure out what's going on with these asteroids. So they start sending out flybys and landers, and I'll talk a little bit more about those later. But they start sending out all these missions of space instruments and space technology to go study these asteroids. Like, let's go see what they're made out of. Let's go find out how big they are, like more information about their masses. Let's see what's going on out there. So they did all of this stuff, and this has been super helpful to know about what's going on out in space. What if something is going to hit us? What does that potentially look like? What is it formed of? What is it made of? All of that good stuff. And then in 2017, this guy entered our solar system. And you might have heard of Oumuamua. Oumuamua was an interstellar traveler. So Oumuamua came into our solar system on a hyperbolic orbit. So instead of being like a comet or an asteroid where they're orbiting our sun, this guy just kind of came in, kind of like catapulted itself off of the sun, and then sped out, left our solar system on this hyperbolic orbit. So its orbit will never close. So it's just kind of stopping by. But this is the first time we've ever seen this. And that's a little concerning, some might say, because not only are we worried about all of these asteroids in our own solar system, we also now have to be kind of worried about these guys. Like, where are those interstellar objects coming from, and how many of them do we have to worry about? Like, is this happening a lot and we just don't see them, or what's going on? So I also, along with this timeline, want to show you this clip, and it's our asteroid discovery over time. So we're going to start here in 1970, and we're starting on this counter of about like 4,000 known 1970. You'll see we'll get to the 1980, 9,000 known here. And then things start to pick up a little bit right around here. So all of the white flashes you're seeing are new asteroids being discovered. And as they're discovered, they turn green. So they flash when they're discovered, and then they turn green. And that's a lot. We're starting to get to 600,000, 700,000. We're at over 1 million known now. So this timer stops in 2015. We now know about over 1 million asteroids in our solar system. And I can see why someone would be concerned about this, because 1 million of these objects that killed the dinosaurs are just kind of hanging out there in space, not that far away from us. So yeah, let's see. So this is what we see as astronomers when we're observing an asteroid. So when we get one of those detections, this is what we see from our telescopes. And it's this little white dot, kind of like just a little speck that's moving through these frames, circled in yellow. And this doesn't give us a lot of information. Like, it gives us a good amount of information. We can figure out how fast these asteroids rotate from this. We can figure out a little bit about what their surface is made of, so we can do some spectroscopy on them and see what the light that's reflected from the sun is, and see a little bit about what they're made of. We can get an estimate on their size, but it's kind of hard to get a full mass, a full size on them. And what we really want to know is what it's made out of. We want to know how dense it is, how tough it is. There's still a lot of other information we want to know about these things. So in order to get past what we can just see from the ground on Earth, we have to do some flyby missions. So this is what I talked about a little bit earlier, where we have to go out there and see what these things look like up close and personal. This was the first asteroid flyby mission. It was included in a mission that was going out to see Jupiter, the Galileo mission, and it just flew by this asteroid Ida in 1991. So that was pretty cool. We were able to get some nice images, some nice information on what this asteroid actually looked like and what it kind of was made out of, and have some better ideas of what's going on there. Then this mission in 2008, the Rosetta mission, flew by the asteroid Lutetia, and that one was pretty cool. I think this was a bit, I don't think these are to scale, but it was a bit bigger of an asteroid. And then back to 1998, the Braille, or Deep Space One flew by the asteroid Braille. So quite a few more flybys. We've had quite a few more since then. But this is just something cool that we're able to do. A lot of the times, if we're sending out spacecraft to look at things that are farther out in the solar system, we'll often use some of that time to fly by some closer things and see what's out there and see what we can learn about them from just looking from a closer view. We've also had quite a few landers, which is, I think, a lot cooler than just a flyby, getting to actually touch these asteroids with a machine, but something from Earth is touching them. The first touchdown was near Schumacher, which touched down on Eros in 2001. So here's a really cool video of that. It's not, I mean, it's 2001, so it's not super high resolution, but you can see here, it's just gonna touch down and then we lose camera. A lot of the times when we're trying to hit things and we don't know super well how big it is or what's going on, we just kind of smash into it and hope for the best. So you oftentimes see things like this where you lose camera at the end of a video. Not great, but it's super cool. We can see kind of a way closer look of what's going on the surface. You start to see these like rocks that you couldn't see from those far away images. And we start to figure out what these asteroids are really made out of. And then there was the Hayabusa 1 and 2 in 2000, or they were sample collection missions. So we kind of touched down, grabbed some stuff from these asteroids from Itokawa and Ryugu, and those were delivered back to the Earth in 2010 and 2020. So we have some really cool samples of these asteroids. And most recently, my favorite mission, just because it comes with a cool video, was this OSIRIS-REx Bennu mission. It was a touch and go mission, and the sample has been delivered now. But here is the super high resolution video of us touching down, and then you'll see it hits it, and then it kind of just gathered up all of that stuff in this bag that it's got on it, and it brought all of that stuff back to Earth for us to look at. So we've touched these asteroids and seen them really close. But that's still not everything we want to know about them. There's still a lot that's left behind. I mean, it'd be nice if we could like take one of these and just take the whole thing and break it apart and see what's going on, but we can't do that. So there are 3 types of asteroids, and that's something that we've learned from all of this information that we've gathered from these missions. The first is the S-type. It is a rocky asteroid. These are stony textured. They contain lots of silicate materials, irons. They are basically just big, dark rocks out there. Not too fun. And then there's these carbon ones, the C-types. These are dark also, but these are carbon. They kind of look like charcoal. So similar in like darkness, stoniness, but they look a little bit darker and different than the S-types. And then finally, we have the M-types. These are metallic. So these are really shiny. They contain a lot of nickel and iron, and they look like steel. And these are really important things to know about these asteroids, because if we're worried, like, what's going to hit us, what's out there, what could possibly become flying our way, we should also know what it's made out of. Because things like density, things like how well it'll break apart, make a big difference in if we can do something about it. They also, like I said before, come in tons of different sizes. So this is the biggest asteroid, Vesta. And then there are tons and tons of tiny ones. And there's a little tiny white dot here that you guys can't see. I can barely see it. But that is one of the really tiny little asteroids. And this is just to show that not only are they different materials, they're also way different sizes. It's kind of hard to put all asteroids in one bin together and say that's the same thing, but we do it. And so what kind of impact do these asteroids have on us based on their size, based on their makeup and their material? Well, this is a little bit of a sad plot if you think about it, but this is our diameter of our asteroid versus the fatalities per event if it were to hit us. So sorry about that. It's going to get a little sad for a minute, and then it'll get better. I promise. Bear with me. So in purple, we have these triangles that show the ocean impacts. So those are things like tsunamis, things that would cause fatalities from that. Then we have in blue the land impacts, and the red line is the summary of all of it. And what I want to point out here is that at about 1 kilometer, right after 1 kilometer, things start to spike. And so that's when we have our really like devastating impacts. That's when these asteroids get so large that they're like extinction event, population killers. That's what you're worried about. It's not, you shouldn't be that worried about it, because looking at like in numbers, we have mostly our near-Earth asteroids that we know about as of 2024. The majority of them are smaller than 140 meters. So the majority of them fall somewhere over here. It's still not a great number. I'm not going to act like this is good. That's like 10,000 fatalities, but it's not a population-ending event. We're not like completely destroying everything on the Earth. People are still, some people are still okay. But and those that are really large, those really large asteroids, those are only less than 20% or 2% of those asteroids are larger than a kilometer. So this is like not a lot of asteroids. Remember I said earlier that like size is going to play a big part in this, is that there aren't a lot of big asteroids that would actually like do a lot of like destroy our, evict us from Earth. So it is something to be concerned about, but it's not likely that it's the end of the world, literally. So with all of that being said, what do we do when we're in this situation? I mean, do we act like this guy and we're like, it's the end of the world? We could do what all of these guys did, which like I don't know if that sending people out to stop the asteroid, if we can kind of turn it around that way. We could not believe the astronomers. That's always an option. It's just to be like, no, you guys are making that up. That's not real. I guess that's an option if you would like to do that. But I, as an astronomer, would hope you would believe us. But it kind of leads me to my main science question here is, will we be able to deflect an incoming object? So like one of these objects is coming into us, and the big question is always like, well, what do we do? What does NASA do really? But what do all of hopefully the space agencies get together and figure out to do about this problem? And NASA kind of tried to answer that recently with the Double Asteroid Redirection Test, or DART. So I want to break that down in a second, but first I just want to, so DART launched, it's this big spacecraft you see here, and DART launched in November of 2021, and it impacted in September of 2022. So it didn't take long to get there. It was a near-Earth, DART targeted a near-Earth asteroid system that we'll talk about in a second. And the mission goal was to demonstrate asteroid deflection with a kinetic impactor. What does that mean? So double asteroid, we'll break this down into bits. To talk about a double asteroid redirection test, I want to first talk about what would happen if we maybe tried to deflect or redirect a single asteroid. So let's just look at a single asteroid, and what happens if we just send something big out there and we hit it and we break it into like 5 bajillion little pieces, and then this probably is what it looks like. There's a reason we don't do that, or we don't think we should do that, and it's because that a bunch of little pieces of asteroid all over the Earth is not any better than one big asteroid in one spot. Like, that's not a good solution. So what we do too, and that's because if we just hit one asteroid that's orbiting another asteroid, if it breaks into a bunch of pieces, because of the conservation of angular momentum and the conservation of energy, it's going to stay. All of those pieces are just going to stay orbiting the bigger one. So if we do one asteroid with a little asteroid orbiting it, we hit the little asteroid. If it breaks up a bunch, because remember, we don't know what these things are made out of. You saw that picture I showed you of like what the astronomers actually see. We don't know really how well, very well what these things are made out of. So if we just hit one that's going around another one, then all the little pieces will stay there. And that's how we like it. So the redirection test part of this, again, we're going to stick to what happens if we redirect a single asteroid. So let's say us here on Earth, we see this asteroid, okay? It's got some orbit, and we're going to try to like change the orbit. But remember, we don't know what it's made out of very well. Like, we haven't gone there and gotten a sample. We haven't like cracked it open and seen what's inside to know what's inside of there. So determining how hard we should hit it, how fast we should hit it, those kinds of things, what we should hit it with, make a big difference in what's going to happen to our asteroid. So let's go ahead and let's just hit this single asteroid, because why not? Okay. Oh no, now it's coming to us. That's like not great. So maybe we should stick to our double asteroid thing, where we have this big asteroid, a little one's going around it, we hit it, if the stuff comes off, no big deal, it's going to stay in that orbit, and if the orbit changes, that's okay, because again, it's going to still be orbiting the big asteroid. So we don't have as much to worry about. Like, this is a very low risk situation right here with our 2 asteroids and our double asteroid test. Okay. So the original orbit of this system, that is our DART target, it was 11 hours and 55 minutes. And the goal of this mission, remember, was to change the orbit with a kinetic impactor. And the goal was to change it by about 7 minutes. So we thought, like, by what we know about physics, which I would hope is a little bit, if we hit it and then with some force, it'll change by about 7 minutes from all of our models and everything. And we thought we knew that pretty well. We knew Dimorphous really well. So Dimorphous, we know, is an S-type asteroid. Remember, the bigger the object, the better we know about it. So S-type, we knew that one. It's really big. This is like to scale. Dimorphous was a bit of a mystery, and this is the one we're hitting, so that's a little stressful. We know that they're like these sizes, but we didn't know what Dimorphous was made out of. We don't live in New York or Paris, so I'm going to give you guys, do you guys know this building? And I think it's in Midtown. It's the Marriott Marquis. And then this Armada bus over here. So basically what I'm saying is we're going to hit the Marriott Marquis with a MARTA bus. I think that'll work. And we had our models like pretty good. So we thought if we do this thing, this is like what the ejecta will look like the stuff that comes out of all the rubble and things that break out of this asteroid. We think that's a pretty good idea of what's going to happen. And we weren't too worried about this because we know it's not going to hit Earth. So like there is no threat at all to Earth in this situation. There is a bit of like overlap because this is a near Earth asteroid system. There's a bit of overlap with Earth's orbit, but that's what we want because we want it to get close enough to be able to like observe it the best we can from wherever, from the ground, and get the most data we can out of this situation. But we knew no matter what we did, nothing's gonna come back and hit us and be a concern. So that's great. Let's go ahead and land. Hit, smash. Yeah, so again, we lost our camera. I don't know if you remember that scene from earlier, but when we hit things, I mean, you just lose your camera. That's fine. So after this impact, after all of like the debris clears and you can see what's going on a little better, so this is October 4th. I think it hit September 28th or something like that, around this time. We take this image using radar observations, and this is where we expected, in the blue circle, that's where we expected the asteroid to be based on its orbit before we hit it. So if nothing had happened, if it was like way denser than we thought and it didn't break apart and we just like barely tapped it, it would still be there. The big white smudge is Didymos there in the middle. And then the green is actually where the orbit is, where the asteroid is, the Dimorphous. So you can see, like, it did something. Immediately after, you could see that the position was changed, and it was in a different spot than we expected it to be in. So it must have done what it was supposed to do. And it did for the most part. So again, here's our original and then expected orbit situation. Remember, our original orbit was 11 hours and 55 minutes, and we expected it to change by about 7 minutes. It changed by about 33 minutes total, which is close. Like 7, 33, it's like a factor of 4. Like in minutes, that's like the same thing. It's close, and it's why we did this. So the reason we did it around a double asteroid system is because we knew that we might not get it perfect the first time. We might not get it perfect on the 10th time, but we did something, and it clearly, I mean, it did better than we expected it to do. If the goal is to move your asteroid, and we can move it more than we hope to move it, then like I wouldn't be mad about that. It's farther from Earth, right? So we did that, and that was really, really great. And we also got some other cool pictures because you guys saw how the camera just kind of was smashed. They thought about this. They didn't just for like, well, I guess we can't have any pictures anymore. That sucks. They sent this thing, which is called the Lycia Cube. And this Lycia Cube is just the camera. So they sent that out there with DART, and it got pretty close. It stopped a little bit before DART stopped, and it just observed the impact. It just watched and sent back the video of what was happening from afar. Here's that video of what it took. It's not a great video, but there it is. It wasn't anything crazy, but you can kind of see in the beginning, it happens fast. It's like the second. I want to go back and show it again. Okay. There you go. Like that big flash right there at the beginning. That was when it happened. And this is all post-impact. So you can see like plus 2.2 days and all of that. And that's just watching it, seeing what all of that debris, all of that impact rubble does, and observing like how that changes over time. And when it calms down, when it stops being a big flurry of rubble and everything. And yeah, we can see that here about like 18.5 days after, it's kind of calmed down. Like we don't see all of that stuff anymore, which is pretty cool. Another thing that we learned, that was bright. Another thing that we learned here is that we learned that Dimorphous is actually a rebel pile. So if you remember before, we didn't know what Dimorphous was made out of before we really hit it. And we learned that it's pretty much just a big rubble pile. So probably one of those S-types like Didymos is. And we also changed the shape of the asteroid. So there's a big difference here, but you get before it's like this oblate spheroid, and so they say after it's a triaxial ellipsoid. I don't know if I see. There's a little stretch over there, but it is cool to know that we can change the shape of this asteroid if we just hit it hard enough. So that's pretty cool. And now we can kind of answer our question, which is, are we able to deflect an incoming object? Maybe. It seemed to work, right? Like, I can't promise you 100% that if some big object is hurtling towards Earth and we have X amount of time to do something about it, I can't promise you that, like, NASA has something prepared for that. They might. They haven't said that they do, but they might. But like, we know that we can push something really hard and it'll move, and that seemed to work with this asteroid situation. And it also taught us a lot about the fact that the asteroid will likely move more than we thought it would. So they said that that was because a lot more momentum came from the ejecta all of that material that was ejected from Dimorphous than what was expected. So we've learned a lot of information from this test, and whether it's done again, I don't know, but I think it would be worth it to explore that, and I think that we can actually maybe do something about deflecting an object. Unfortunately, we have to answer a second question here, which is that will Earth be hit by an asteroid? Because like that's your question after this, right? Is okay, well, we can maybe do something about it, but is it gonna happen? Should we be concerned? So there's this thing called the Asteroid Terrestrial Impact Last Alert System. And this is ATLAS. Some of you might have heard the word ATLAS recently. We'll get to that. But here is ATLAS 2. It's on Mauna Loa in Hawaii. It's a kind of telescope system that is spread out throughout the world with like four, they might have added some more different telescopes. And this is one of them. So they're not huge telescopes, but they get the job done. They do their job. And this is a video it took of Dimorphous and Didymos when DART impacted. So you can see it gets brighter. So that's really cool. Like we observed that with this telescope. And the cool thing about this system of telescopes is that all they are doing is every night they are observing the sky and tracking asteroids. And they're looking for new asteroid detection. So they're just looking for those new little blips of something moving and trying to see if there's any new asteroids we didn't know about before. Remember, there's over 1 million asteroids total, so it's not unlikely that there are more, but they're looking. And the good thing about this system is that it is specifically to alert us if it finds an asteroid that has any potential of impacting Earth. And so the amount of time that it'll give us on that alert depends on the size of the asteroid mostly. So a smaller asteroid will have less time to prepare because it's harder to detect. I think it said about a 2-meter asteroid, we'd have about 2 weeks. And then a bigger asteroid, maybe about a kilometer-sized asteroid, I think we would have like a month, 2 months, something like that. So it's there to alert us. If whether we choose to be prepared about that or not is not up to us. But it's there to alert us, and that's really nice that we have that system in place. And so it did actually detect an asteroid that had a very small percent chance of hitting Earth. This is 2024 YR4. And so it's like that little box up there zooms in, and then this is our little asteroid guy. This was a pretty small asteroid, and when they first released the alert, it was that ATLAS has discovered 2024 YR4, and it has a 1% chance of hitting Earth in 2032. Then a year later, they were like, wait, never mind, that's not going to happen. Actually, don't worry. No impact threat. I think the threat now is like 0.000008 in 2050 something. So we really have nothing to be worried about at all with this system. If you've heard about it, if we want to look at like what that impact would be, this asteroid is 0.054 kilometers, which is about 50 meters. And so if we draw that on our diagram over here, I think that's about 1,000 fatalities if it were to hit Earth, and it's 0.0008% chance. So it probably won't hit Earth. If it does, it's not going to take all of us out. It's going to be okay for most of us. Again, sorry for those 1,000 people, but it's not going to get most of us, which I think the main thing to avoid here is like human extinction. That wouldn't be great. So then there's this guy who, has anybody here heard of 3i Atlas? Can I get like a show of hands? Yeah. Okay. Can I hear like what somebody's heard about it? Like,
it's a mothership.
Yeah.
Aliens.
Aliens mostly. So did you guys see anything like this? I liked this one. So it says James Webb Telescope stuns scientists with first ever image of mysterious 3-1 Atlas object. So first of all, that's not the name. Second of all, this is the JWST photo. Like, this is the James Webb actual photo. So be careful. There are no aliens in this photo. I mean, I don't see any, and I look at telescope images quite often, but I don't see any aliens here. I do see maybe a little bit of a tail here. So 3i Atlas was actually characterized as it got closer to us as a comet instead of an asteroid. But this is another one of those interstellar objects that's like Oumuamua that we saw at the beginning. Also might have been called an alien traveler spaceship, something like that. Motherlord ship, I heard. I also saw this. NASA in panic. We are arriving. They are not arriving. So 3i Atlas is not going to hit Earth. And as far as we know, as far as we can tell, it is not aliens. At its closest approach, 3i Atlas will be 170 million miles away from Earth. And that's going to happen about a month from now, which is pretty cool. It did just make its closest approach to the sun recently, I think about a month ago. And there's nothing for us to be concerned about this. It's not going to hit Earth. Like I said, it's another one of those interstellar objects. So they are just really cool to study. We can find out about what rocks are like outside of our solar system. It's got this big hyperbolic orbit showing us how it's going to travel in and out of our solar system. And by Christmas, you'll be saying goodbye to the aliens in this spaceship, I guess. But yeah, by Christmas, it'll be gone. It won't be gone, but it'll be leaving our solar system on its way to maybe another solar system. So definitely not aliens. Pretty cool stuff, though. This is another image that was taken recently of 3i Atlas. You're probably going to start seeing a lot of these images because it's getting its closest approach to us. So the closer it gets, the better images we can take of it. And I think I saw some new ones today too. This is from a virtual telescope project in Italy. But yeah, so there it is. You can definitely see its little like comet tail happening there now, which is pretty cool. This looks like it was a pretty long exposure to get that, but yeah, we have some pretty cool pictures of it now, which is nice. And something I want to say here about like these percentages that you get, these like chance something's gonna hit Earth. A lot of this relies on its orbit. And the reason I say that is because you'll see here, so here's Earth in the middle, and then we have this like object coming in. And it starts with this short orbit. That's probably where we detect it at. So eventually it gets close and bright enough that we are like, oh, we see an object there as it's getting closer to us. And then at that point, we don't have a lot of data on it. We have a little small piece of its orbit. We have like this much at a time. And so over time, we're able to track that orbit, get a better idea of what that orbit is. There are less options for what the orbit could be. So like if you start off with a small piece of a circle, you can draw a lot of different size circles out of that. Whereas if you start off with a full circle, that's what you've got. And so all we're doing is we're starting off with a small piece of a circle and saying, we don't know exactly where this is going to go, but there is a chance that that orbit ends up being towards us. And then as we get more data, which doesn't take that long usually, about a year before we can be certain that it's not going to come towards us, we have a better orbit and we have an idea of where these objects are traveling to and where they're coming from, what they're made out of, and all of that just comes with time and having more data. So when you see something that's like 1% chance, it's usually a new thing and not something that we have a lot of data on and not something to be very concerned about. So will Earth be hit by an extinction event-sized asteroid? I think the question changed a little bit from last time, but that's okay. Probably not. Like, remember how I showed you earlier that like less than 2% of asteroids are actually extinction event-sized asteroids? And then I showed you that like we don't have any right now of the millions that we know of that are like planned to hit Earth anytime in the near future. So we probably won't be hit by one. Now, I can't say that there's not another interstellar object that won't enter our solar system. I know these are kind of not answerable questions, but the statistics are on our side. Right now, we don't know of anything that's going to hit Earth. Three-Eye Atlas is not aliens that are coming to invade us. We would be able to probably deflect something if it was going to hit us. And we're keeping track of all of these things and collecting the data and figuring all of that out. So with that, I want to bring us back to our timeline that we created earlier, and we can add some things to it now. So we can go ahead and add our DART impact, our very successful DART impact back in 2022. We can add our Lucy mission, which is a newer mission to do a bunch of asteroid flybys. So basically, they picked a bunch of really interesting asteroids, and this mission is just going to fly by, I think, 3 different asteroids. Some of them, like this one, is in a like triple system where it's got an asteroid and a little double pair next to it. That was really cool. And this is going to, it already flew by those. I think it flew by the second ones, and it's got at least one more that it's going to pass by and take some images of. We also have the Psyche mission, which was launched and is planning to fly around the asteroid Psyche in 2029. So this mission is going to like just orbit one asteroid over and over again and see what we can learn about it from doing that. And then something really cool, it's 2027, which is not in the right technical order, but that's because this is like a planned thing. So right now it says not before 2027 is the launch date. But this is NEO survey. It's the Near Earth Object Survey, and it's the first space telescope mission designed specifically to observe and explore asteroids. So that it's going to specifically survey the sky, look at as many objects as it can as quickly as possible, and observe lots and lots and lots of asteroids and track them, which is going to be really cool. Let's see. And so the last thing I want to show you is something that's coming up very soon. It's already started. So this is images from the Rubin Observatory down in Chile. And what you can see here is that it is tracking asteroids every single night. So the Rubin Observatory has a survey where it observes kind of like, it's going to observe the entire sky over 10 years in like basically deep field images. And over that time, I want to play it again. Over that time, it's going to look at probably millions of asteroids that it's going to be able to track for us. So these are just these little blue dots. It's just showing you all of the asteroids that it tracked. It discovered over 2,000 new asteroids in a 10-hour observing period. So by night 7, all of these observations in that one part of the sky gave us 2,000 new asteroids. And it's going to be looking at the sky for 10 years. So I think we're going to find a lot more asteroids in the near future. And I think we should be looking out for that kind of thing and learning more about their orbits and what's going on with them. So with that, I will take questions.
already made an Armageddon reference, so I'm bone dry on references. Any questions from anybody?
So, in your professional opinion, should we put something up there now, like in between Earth and Mars, that could be directed at an asteroid with less time ahead of time?
Yeah. Can I? Yeah. Okay, so the question was, should we put something up there now? That's a lot of space to cover. Literally, so just anywhere between Earth and Mars is.
Within orbit of Earth.
Yeah. I don't think it would hurt, but I also don't think it didn't take very long to launch and get to like the Dimorphous and Didymos system. So like, I don't think it would hurt to. I think if we could figure that out, that would be good. But I guess then it depends, like, we've got to time it right, of like, which we'd have to do anyway, of like, it's orbiting Earth and then it's also an asteroid coming at us in a certain spot. I feel like we have more range if we just keep it on, like, prepared on Earth and then just launch it when we're ready. I don't think it makes that big of a time difference to just launch it from Earth versus a probably like low Earth orbit. Does that answer your question?
Yeah, I'm just thinking the earlier we get to it.
Yeah, always.
If there's money to fund something to put between us and Mars, I have other thoughts about what that money could be used for.
Hey, thank you so much. Super, super interesting. I had maybe a boring question about the classification of them. How do we know if we found a new asteroid that is a new asteroid? There's a million of them, and a lot of them are so tiny. How are we classifying the look and feel and shape of everything?
I asked the same question when I was a graduate student. Your boss can answer it if he wants to.
I'm going to do my best, and if Todd wants to say something else, he can.
I'm not the speaker.
So, from my understanding, we follow these things for as long as we possibly can and trace out their orbit. And then we have a good idea of, like, it should be coming back. I feel like the problem, like, there's always the possibility it has like a run-in with something else out there in the asteroid belt, and then it's hitting things, and like, the best we can do is like track it while it's in our sky. If it comes back at, kind of the exact same orbit, then we know that's the same asteroid. But if not, sorry, bye-bye.
You don't have to bring it up. Okay. That was a great talk. I didn't know you were ready to be a stand-up comedian. Question: if you were going to have not one but two telescopes available to you for 3 weeks in December, and 3i Atlas is there, and it's bright enough, and it's at the right RA and depth, what observations would you make? Because I just started thinking about it.
I don't know. I feel like they're observing it from everywhere, Todd, but there's always, like, rotation is great to get. So you can get variability, I guess, from that, but it won't tell us much more than the rotation. Well, I would use one of the telescopes to get spectra. Sebas is yelling at me in the back. He's like, use Chiron, use Chiron.
So I can imagine.
Am I missing one?
No, I'm just wondering, just starting to spin my wheels on it. We could get a spectrum every night, and we could observe it photometrically at the same time.
Yeah.
Every night. Because we have two telescopes right next to each other and two observers who have complete flexibility.
And somebody who's going to be there during its closest approach.
Right.
Get a room, you two. Anybody else have any?
I would accept any ideas from anyone about how we can do this the best, because it could be fun.
We'll take one more question. I'll go up there.
No, it's okay. I can do that.
All right, you're
So I think if I were doing it, I would undershoot. I mean, it's always good to like have that situation where it changes its orbit a lot, but then there's always the situation where it's more it's less massive and less dense than you think it is, and you break it up and then it's still coming towards us. So if it were me, I would hit it less hard than you think you need to hit it. But as far as like a real plan, yeah, I mean, as far as I know, I don't have direct communication with NASA, but that's the best we got.
Because I do. Have you ever thought about training drillers to be astronauts as opposed to training astronauts? Just put a nuke in it.
Just put a nuke in it.
The American way. And with that, thank you everybody so much for coming.
Justin volunteers.
We would love to show you Saturn and some other stuff, but there's some clouds. So I'm sorry. Please join us again in December when we'll come back and hopefully show you some cool stuff. Thank you, everybody. Great job. Great
Thanks.
job.